Good evening. My name is Luis Alberto Quispe Malpartida. I'm a graduate exchange student at the Universidade Federal do Rio Grande do Sul in Porto Alegre, Brazil. And today, I will deepen the physical and mathematical understanding of the heat conduction equation in cylindrical coordinates. Heat conduction is the process by which thermal energy is transferred from a hot source to a cold one within the same body or several bodies in contact with each others. In solids, molecules or atoms begin to vibrate rapidly when heated. This vibration energy is transmitted between the molecules that make up the solid. This microscopic process results in the flow of heat from areas of higher temperature to areas of lower temperature. Heat conduction is described mathematically using the Fourier's law, which will be used later in this study. To develop this equation, we start from three main hypotheses. First, consider that the medium is continuous. That is, the physical properties change continuously and gradually in space. Second, consider that the medium is stationary. That is, the temperature doesn't vary with time because the volume of variations produced by the change are smaller than the volume of the body. Finally, there is no latent heat, which implies that the heat flow doesn't cause phases change in the material. That is, the heat transfer only produces a temperature variation without transformations between solid, liquid, or gas. The following figures we adapted from Incrospera's book, Fundamentals of Heat and Mass Transfers of 2011 versions. Figure 1 represents the cylindrical object that we are going to analyze. Using cylindrical coordinates implies working with three spatial components, the radius r, the angle phi, and the height c. On the other hand, in figure number 2, we observe a differential control volume. It's possible to see heat fluxes at both the inlet and outlet, as well as differentials of the control volume. Now, we proceed to perform an energy balance in the control volume. As can be seen in equation number 1, this is mainly composed of input energy, generate energy, and accumulate energy. The accumulate energy is the result of addition and subtraction of the three types of energy mentioned before. The input energy is equal to the income heat flows in figure number 2. The generate energy is the product between the heat flux and the variation of the control volume, which can be expressed as shown in equation number 3. The output energy is composed by the sum of the heat fluxes at the exit of the solid under analyzed, as shown in figure number 2. The accumulated energy is the density of the material multiplied by its heat capacity and the variation of the control volume. To determine the heat transfer rates in each other direction, we use the Taylor series expansions, as shown in equation number 6. This allows us to express the difference in heat flux between the opposite phases of the control volume. These equations, number 7, 8, and 9, are replaced in equation number 4, thus obtaining expression number 10. This one. Okay. Then we replace equation number 2, 3, 5, and 10 in equation number 1, obtaining equation number 11. This one. As we can see, this equation can continue to be simplified, thus obtaining the expression 12, which is already a simplified form of a heat balance in cylindrical coordinates. Now we introduce Fourier's law, which gives us a relationship between heat flow and temperature gradient. This law is fundamental and mentions that the Heat moves naturally from regions of higher temperature to regions of lower temperature with a rate proportionally to the thermal gradient. First law is equal to the product of thermal conductivity of the material, the area, and temperature variation with respect to time. Applying this law to the radius r, angle phi, and height c directions, we obtain equations number 13, 14, and 15. Then these are replaced in equation number 12. And after that, after a simplification, we obtain expression 16. Finally, we multiplied the equation 16 by 1, between the volume, the volume differential, obtaining expression 17, which is known as the heat conduction equation in average steady state regimen. In the result obtained from the heat conduction equation, we can observe that the property of thermal diffusivity can be introduced. Thermal diffusivity measures the capacity of the material to conduct thermal energy in relation to its storage capacity. It is represented by the letter alpha and is defined as the ratio between the thermal conductivity and the product of the density of the material and the specific heat capacity, as shown in equation 18. In table 1, shows three different states of matter: solid, liquid, and gas, with their respective diffusion values. For gold, it presents a thermal diffusivity value of 127 square micrometers per second, while for carbon monoxide and engine oil, it presents a value of 21.3 and 8.56 square micrometers per second, respectively. Conclusions. The heat equation obtained is also valid for a stationary medium where the control volume is defined differently and the energy balance is also different. It's possible to adapt the heat equation to specific operating conditions. For example, it is possible to simplify the equation in case where the regimen is stable or internal energy generation. The control volume or heat conduction is one or two dimensional. It can be applied to the distribution of temperatures within a body, knowing how is the temperature distribution occurs. It is possible to study how certain material behaves in relation to a thermal output or how phase change occur in a material. In addition to that is that equation used in research projects in evaporation or refrigeration systems. With this, I'm concluding my presentation. I appreciate your attention and hope this review has clarified the importance of heat conduction equation in cylindrical coordinates. Thank you so much.